Hello and welcome to this short tutorial on how to set up a population balance model in ANSYS Fluent. So for this problem I'm using a stir tank reactor. We are not really implementing any reactions, but we have a two-phase model, basically a multi-phase model using the Eulerian model in ANSYS Fluent. So to give a brief overview, this is our geometry which was adapted from ANSYS Fluent ANSYS library actually, and I added a few inlets for water flow. So water is the primary phase in this model. It's allowed to move from the top, as you can see here, from this inlet. If I can properly select it right here. So this is the inlet for water, and then the outlet for water is mainly at the bottom of the domain. And we also have a stream of air, which is our population balance phase model. Air is injected at this inlet down in the bottom, close to the impeller. And then it's allowed to flow out of the system through the top of the domain. So I set this the top of the domain as an outlet boundary condition as well. So this is what we have in this sketch, in this schematics, showing where air is added into the domain. But here we're not adding air as a continuous, it is a continuous phase, but it's not being added in the same way as water. It's added as a population balance phase, which means we are considering air as droplets or bubbles in this case. So the population balance model is a popular option for modeling things like droplet dynamics, as well as particle dynamics, either solid or liquid or gaseous particles. In this case, we're modeling gaseous air bubbles in water. So the population balance model that we are implementing has basically two phenomena that we are incorporating: the coalescence of bubbles, smaller bubbles forming bigger bubbles, as you can see here. And we can also have a breakage, which is when you have a high enough shear stress that a bubble, instead of just deforming, will actually break into two bubbles, either two like one big or in a smaller bubble, or in a different profile. And this is implemented within Fluent using the PBM model, population balance model. So basically, the population balance model is an Eulerian based model where you're tracking a population of particles at each cell. So you're tracking concentration based number of particles per unit volume, and you basically have models to account for how they grow, how they form, how they shrink, or how they can even disappear. So the frequency of aggregation, and here aggregation is used as a synonym for coalescence or agglomeration, and breakage or rupture as well, or division of particles, or in this case bubbles, can be determined by the physical conditions in the fluid around it, the water phase, as well as the intrinsic properties of the bubbles. Things like surface tension, for example, have an impact. So basically this is the PBM equation that we are implementing in a simplified form, and more detail can be found in the Fluent Theory manual, which I highly recommend looking through if you want more information. So the population balance model that we implemented follows a discrete method, which is basically a model whereby we're tracking the bins of particles at different sizes. and I'm going to show how that looks like in Fluent. Basically, so the first thing is once we load the model, and I've already done this part with the mesh. Um, so this is a relatively simple design with one impeller. Uh, you might see situations where there might be several impellers, much more complex geometry than what we have here. So basically we have an impeller in the center near the bottom of the domain. And let me show the tank as well, so you can see the impeller with the shaft. And around the impeller you have the MRF body, which we will use to implement a moving reference frame, so that we can implement motion basically within our model and shear stresses that will affect the flow profile within the tank. So once the model has been loaded in the mesh, and this is a relatively simple mesh to implement, simple geometry to mesh, we can add the materials. So I would first add air. So air was already the default. I added water liquid from the Fluent database, which you can go by clicking air and click on Fluent database and then select water liquid, and then you can just copy. So I didn't change any properties for water liquid or for air. It's a relatively simple simulation just to show an example. And then I come into the model, the multiphase model here, and then I select Eulerian. I've already done that, and I left the default as implicit, and number of Eulerian phases to 2. So we have 2 Eulerian phases, and the first phase is water liquid. We can rename that to water, or we can keep it as it is. So in the phase 2 is air, and here it defaults to a diameter of solder meter, basically when you activate the population balance model. And then let's go to the phase interaction tab, where basically you're looking at the interaction between the two pairs, basically the pair of phases. And there are many things that you can add or add to your phase interaction. There are forces, there are heat and mass and reactions as well, and there's a lot of things that we can explore here. But for now, I kept it very simple. I kept the default Schiller-Neumann drag coefficient, and I added surface tension coefficient for air and water of 0.072 newtons per meter. I could have added lift coefficient as well, and virtual mass coefficient, but ideally, like for the initial stages of modeling, of running the simulation, it would be ideal to keep it simple, and then once we get closer to convergence, we can start activating more complexity to our model. Finally, the population balance model. So this is a tab that's available. It's set to off by default, and to activate, you just select one of the methods. Here I selected the discrete method, which I mentioned before. It's basically you're tracking bins of particles, and each bin has a specific size. And to know basically what size you want, or what size is physically reasonable, you can select the size calculator here, which will provide you some ranges for minimum and maximum values for bubble size in this case. So it accounts for the properties of the primary and the secondary phase. And then I click calculate, and it will tell you about the minimum empirical limit for calculated diameter. So I selected that value here, and I also used a value in the maximum diameter, somewhat closer to the maximum stable bubble size based on the capillary length. However, it's a bit higher than that. To change the maximum diameter, you can change the number of bins, or you can change also alternatively the ratio exponent. And if I change the ratio exponent here, for example, if I go to 1.4, it's going to automatically change my maximum diameter as well. So I can go back to 1.2, and then we can activate the phenomena. So the phenomena is basically all the kinds of changes that can happen to your bins. We have aggregation kernel, which is the coalescence between bubbles. Here I selected the Liao aggregation model, which is a popular model that accounts for a variety of physical phenomena to understand, to basically track the aggregation of particles, aggregation of bubbles, so the shear stresses and other effects. And the breakage model, likewise, from Liao, is also a reasonable approach. It's being used in literature quite extensively. So yeah, those are the two models I've selected, and there are a variety of other models as well that you can select. Prince-Blanch, Liu model, as well as for the breakage model. In this case, I don't have nucleation. Nucleation is basically the formation of new bubbles. Or if you're looking at a different application, such as aerosol formation, nucleation would play a role. So here, to activate nucleation, you would have to check this box and either set it as a constant or create a user-defined function for nucleation specifically, and also growth rate. So growth rate is when basically the particles are growing as they, for example, in the case of aerosol, or basically they're gaining mass through condensation or other phenomena. So in this case I didn't activate it because it's not applicable for this problem. So once all of this is set, we can click apply and then close, and then I can close this as well. I should actually go back there. I just want to mention something that's quite important when setting the bins. You can verify the bin size using the size calculator. Sorry, not the size calculator, the print bins. You can verify what are the sizes of each specific bin of particle that you're evaluating. So bin 0 is actually the biggest particle, the biggest droplet size or bubble size. It's around 12 millimeters, and bin 9 is 1 millimeter. The units are in meters. So basically that's very important. In other methods, such as method of moments, like standard moment, quadrature, and so on, these methods, they calculate the particle size distribution slightly differently. So basically they track statistical moments, and there are some pros and cons to each of these methods. I selected 10 bins so I can capture the distribution fairly well. Fewer bins might be more efficient computationally. More bins may be more descriptive, but more expensive computationally. So I can close that. And I set energy as off. I also activated, so I'm using the SSTK omega turbulence model. Basically kept all the defaults except for I activated the dispersed turbulence multiphase model. Basically this model is good for when you have one phase that's relatively small or dispersed, in this case bubbles. So it is a suitable model, and I've observed it helping in terms of convergence as well. So we can click OK here. And that is basically it in terms of the models. And materials, we've defined all the materials already with their expected properties. So now let's go into the cell zone conditions. So the cell zone that we want to specify is the MRF cell zone, the zone in red that you can see here, surrounding the impeller. So we define it, basically if you double click it, you can check frame motion, and you can select based on an axis of origin. You can select the rotation axis direction, so basically that's the axis of rotation for the impeller itself. And so that's set at 0, 0, and -1, and I set a rotational velocity in radians per second. The units you can actually change if you go on domain units. If you select angular velocity, you can actually change to RPM, or degrees per second. The default is radians per second. So for this simulation, I kept it at I set it to 30 radians per second, and the rotation axis direction will help you define whether you're going counterclockwise or clockwise as well. And basically the reason why we choose Z is because we're on the Z axis. That's where the impeller is aligned with the shaft as well. So I also have to make sure that the shaft moves accordingly. So I went into wall shaft here, and then in wall shaft you can basically do something very similar. Axis of rotation is 0, 0, and -1, and the rotational speed is 30 radians per second. So that's all good for now. So once we've defined all of these parameters, what we need to do now is make sure that we define the boundary conditions. So I have basically, as I previously mentioned, two inlet boundaries. One is for air at this tube here that goes close to the bottom of the tank, and for this I don't have any water flowing, so water is phase 1. So water has a velocity magnitude of 0 here. However, phase 2 I did specify a velocity of 0.5 meters per second. We can play around with this velocity to see the effects of bubble size and bubble distribution as well. And if you go into multiphase, you can actually define like what kinds of bins or what kind of bubbles you're going to add in terms of like the fraction of each. So the volume fraction for the bubbles for the PB phase is 1. And I set everything to 10%. So basically we have a uniform injection of bubbles into the tank. And then I can close that. Also, the water injection or the water inlet is set at the top of the domain, as I mentioned, and we can go into phase 1. That's the water phase. I set a mass flow rate of 6.57 because it matches closely with the expected flow rate at the bottom here of water, since we have water flowing at the bottom under a pressure outlet boundary condition. So basically that helps keep the system, the continuity, the mass balance for water in the system. And that is basically it. So I've defined the wall, MRF conditions, both boundaries, both outlet boundary conditions are also defined as pressure outlet. So not much to it, basically using the defaults. And yeah, so basically what I need to do now is also define some report definitions. So it's good for especially checking convergence, and if you want to make some adjustments to the model as well as it goes and increase its complexity and add more physical phenomena, such as, for example, diffusion of oxygen into the water to understand how how bubble distribution, bubble size distribution can affect how much oxygen there is in water. So, and there are other things as well that we could add to make the model more and more realistic. So to do that, I can go into solutions and then create the model definitions here. So I've already defined one, which I can actually show. And I should have named that as diameter. So basically what I'm doing is I'm measuring the overall diameter of bubbles as they emerge through that through this pressure outlet here at the top. So I want to know like how big my bubbles are, my air bubbles are at the wall liquid level, basically at the very top. And to do that, you can choose a field variable into you can choose properties and then diameter once you select phase 2. And this is an area weighted average. So I can click OK, and then I can also create another report definition that's quite useful for these problems. It's good to check on the shaft torque. So I will select moment. I will keep the moment axis as it is. I will write torque, and I'll select the impeller wall as my area where I am evaluating the torque, and then I will click OK. And that is pretty much it in terms of models. So I should also mention that we are running a steady state simulation, and once we are done, we can actually do some post-processing looking at things like the contours for velocity and for diameter. So I created already some surfaces to do that. So I'll initialize the problem and then I'll run. So basically we can see the torque as well as the diameter changing a bit. So I initialize the domain with a small amount of particles, bubbles. That's why we have some change here in the diameter right in the beginning to help with convergence especially. And here are the residuals. So it can take a little bit of time. The population balance residuals can take a while and they fluctuate quite a bit. I've already basically ran all of these models, so I can actually go forward and show what we are going to get once we run them. Specifically for 30 radians per second, and I can compare also with the results that I got for other angular velocities. So here what we see is the contours for diameter at a plane crossing basically the tank. So you can actually see the profile for diameter, where as you go yellow color, it's actually bigger diameter, bigger bubble diameters. Green and blue are smaller diameters. I can look at things like the path lines as well to see where my bubbles are going. So I'm going to track in phase 2. And then you can see, I should actually draw a mesh just so that we can figure out where we are at. So basically you can see that there's a lot of movement here as the gas bubbles get released from their injection point. They get affected quite significantly by the impeller. One thing to note, if you go with a smaller angular velocity. In this case, I ran with 10 radians per second, so a third of the value. What happens is the bubbles just get basically, once they get released from their inlet point, they just go up immediately. So they don't really get affected as much by the mixing action of the impeller. I also want to briefly talk about the comparing the diameter distribution of the bubbles for the different cases. So basically, what we have here is the profile, the contours. Um, we can compare 30 radians per second with 20 radians per second. Again, it's a bit darker green, indicating that it seems to have like a smaller bubbles. Um, so, and if you go with 10 radians per second, you actually get a lot more concentrated plume of bubbles, uh, basically moving upwards. So usually, the bigger the bubble, the faster they go up. Um, so we can also look at things like the velocity profile. Here I set at a limit of 0 to 3 meters per second, so that we can keep a consistent scale. So here is the velocity as well, and here is the velocity, which I should name accordingly. So velocity. So if you go from 30 to 20, so 30, let me make sure, to 20 to 10, you can clearly see that as you increase the angular speed, you get more mixing, more shear, and that has an impact on the collision rate of bubbles, as well as on their probability of aggregation or breakage. And that's what we have here. This is basically the 10 radians per second case. A useful way to evaluate the bubble distribution is using the results tab in the model specific section. You have the option to, the population balance option here, and we're not using moments. If we were using moments, we could check this, but we can go directly to number density since we're using a discrete method for population balance. So here what we can do is we can look at the discrete number density at a surface or for a volume, for example. For instance, if I look at the midplane, which is a plane, basically a plane that's cutting the domain, and I can actually show the midplane is here. So we could actually cut the domains in different sections, like at different heights, and we could actually look at the distribution, for example. We can either print, or we can plot, or we can write it as well, and do the plot in Excel. I can do the plot right here, and you can see actually the distribution of particles, the overall distribution of particles, which is somewhat representative of what we would have across the domain. So basically we have a lot of, and I should also change the x-axis into exponential so that we can read what the diameters are. So basically the smaller diameters are 1 to the power of 1 times 10 to the power of -3, so that's 1 millimeter, and that's the most abundant number of particles that we have, obviously, because basically they, for a specific volume, you would have considerably higher number of smaller, for a fixed volume. Basically, if you compare two bubbles at different sizes, the smaller one will have a significantly greater number, depending on their, of course, on the ratio of their diameters. Here, it's a number density per per volume. So basically we have a lot of smaller ones, and then it decays over time, or it decays in this distribution uh, as we go bigger in diameter size. I've also done this plot and compared 20 radians per second to 30 radians per second. Basically, what we see is for 20 radians per second, we have more of the smaller bubbles compared to the 30 radians per second, which is actually something we observed in the contour plots as well. And however, if we look at the four um, around 4 millimeters, we actually have a larger number of bubbles in the faster angular speed, which may signify that maybe they're concentrating more in a certain region, or maybe they're, because of the shear or the mixing effects, they're not rising as fast, or maybe there's more uh, collision between smaller bubbles leading to the formation of bigger bubbles. So there are a lot of things that we could evaluate here. It's a very powerful model overall, and I highly recommend using it depending on your application. Uh, and yeah, it's very fun. So yeah, let me know if you have any questions, and thank you so much for watching this short tutorial on how to set up population balance models.